Georgion. It is a great pleasure to introduce Professor Georgion for this session 3. Currently, Professor John is working as a professor of chemistry and biochemistry at the City College of New York. Before joining the City College of New York, he held research positions in the Netherlands, Japan, and the United States. His major research interests are organic material chemistry, multifunctional soft materials, surfactants, green amphiphiles, etc. His research group has successfully developed environmentally benign antibacterial paints, polymer coatings, molecular gel technologies, oil spill recovery materials, green battery components, and oil thickening agents. He holds more than a dozen patents. He is a fellow of the Royal Society of Chemistry and a visiting professor at Max Planck Institute for Colloids and Interfaces, Germany. He has received many awards: Senior Fulbright Scholar Award, the Pfizer Visiting Professorship at IIC Bangalore and the Kerala Center Award, and the Tokyo University of Sciences President Award. With this introduction, I invite Professor Georgion to deliver the presentation.
Good evening to everybody, and Professor Begum, thank you very much for your kind and generous introduction. And it's a pleasure to be back to Cochin University. I've been in the campus several times, starting from when I was a student. And I'm very happy, and also I am thankful to the convener, Dr. Sebastian Neibel, and Professor Sri Kumar, and all my friends, including Professor Pradhaban, and that is wonderful. And I'm happy to present some of the research what we were practicing for several years. And you can see my slides right now, or I need to reshare. Okay, I can reshare. What about now?
Yeah, we can see, sir.
Okay, that's great. Yeah, as just like the introduction, what we do is much more of a functional, how we can create functional materials, starting from renewable feedstock. In other words, our interest is to repurpose the molecular building blocks of life. That means lipids, glycans, nucleic acids, proteins. These are part of our life, and we created by this one, and we do a little bit of a chemistry on those family of molecules to produce materials and systems with the controlled structure and properties which are sustainable and green as next generation materials for future. And I am from the City College, and City College is a part of the City University of New York, and the graduate studies or the PhD studies at the Graduate Center. And this is about 24 campuses across the New York City. And as I just mentioned, whenever we create new molecules, they are mostly interfacial chemicals. What exactly mean by interfacial chemicals? For example, I am sure that all of you know this one, lotus leaves. And lotus leaves are known to be clean and pure all the time, because because it's clean by itself, it is a self-cleaning surface. And that self-cleaning surface is created because of the presence of a simple organic molecule self-organized at the surface of these leaves, and whenever the rain comes, the water will flow away along with the dust, and it is always clean. And that cleaning process is happening because of that simple secondary alcohol nicely organized at the surface of the structure. It is highly hydrophobic, and thus it is, water is cleaning away. That is one form of activity of interfacial chemicals. Another, maybe the most recent example, I am sure that all of you know, right now, I don't need to talk about COVID. And right now we have several kind of vaccines. There are traditional vaccines that are mostly practicing right now in India, but the new generation vaccines are mRNA, messenger RNA vaccines. It is developed by Pfizer and Moderna, and you can see this is, the traditional vaccines are mostly the technology by DNA, But the RNA vaccine is these two vaccines. What they try to do is the scientists, they are trying to access the gene sequence of the spike protein from the database. And from the sequence, they generate strand of messenger RNA, and this is the messenger RNA. And this messenger RNA will be in the vaccine, but this messenger RNA is not stable at normal conditions. In order to keep them stable, the messenger RNA falls apart very easily, so it needs to be protected by a tiny ball of fat. And this tiny ball of fat is nothing but lipids. They self-organize to create the vesicles. And here also in the virus, there is a lipid coating around this DNA of the virus. That is exactly the doctors and the health workers are asking us to clean or clean or wash your hands all the time, because those soap can kill the virus. And this is again one of the best example for how interfacial chemicals can utilize for functional utility. And that is another example. We are trying to create something similar in the laboratory, utilizing sugars, fatty acids, lipids, and other kind of natural molecules. This is one example. We are trying to generate jellies and jellos, and for food applications and different other kind of applications. We were doing this kind of chemistry for quite some time, mostly vegetable oil based chemistry. And we are also interested to develop molecules which can respond to the stimuli. And I will discuss about some of these in much more detail. And we recently interested how the seeds, some of the seeds in nature have the capability to gel itself in presence of water. Now chemistry, the chemistry will be done by the seeds itself. And recently, much active area is we are working on how we can generate or create throwaway batteries based on naturally occurring molecules as an alternate for lithium-ion battery. Currently, we are using in our cell phones and wherever it is. But it is much more of a fundamental understanding. And the last one in this case is we are trying to generate molecules. They are highly interfacial active and which could be potentially useful for oil spill recovery remediation, and we called herders. And herders, I will discuss about that one, little more details. And as I mentioned, we are always interested to create molecules from naturally occurring systems and materials. And there are some of the examples. We are utilizing the molecules. We are using cashew nut shell liquid-based molecules. We are utilizing vitamin C. We are utilizing many of the molecules which are present in these different kind of fruits and other systems, and starch and oil and all kind of things. And this is the chemistry we practice. Suppose if you are getting byproducts, co-products, or waste materials from plants and crops. This is plants and crops, and we utilize those basic materials, do some chemistry. It can be traditional organic chemistry or it can be biocatalysis. The ultimate aim is to create amphiphilic structures with a hydrophilic head group and a hydrophobic tail, and this is a typical lipid molecule. Once we have these molecules, the lipid molecules, we can self-organize those molecules in different kind of assemblies. It can be micellar structure, it can be vesicular structure, or it can be bilayer membranes. Even we created different kind of jelly structures, liquid crystals, and solid bilayer membranes, and for sensing applications. And these are all done by self-assembly process. And self-assembly is, the example is one example. One typical, the starting material is cashew nutshell liquid. I'm sure that everybody in Kerala, you know what is a cashew and where it is the cashew nutshell liquid is coming. This is a cashew, the shell. And when the industry, especially in Kollam, in Koilan, all our cashew export, the cashew processing is happening. Most of the factories are there. What they does is typically they are roasted. There are different processes. It is a high temperature process, and during that process, the meta-substituted salicylic acid, there is a COH group here, and during the high temperature process, there is a decarboxylation reaction happens, and this meta-substituted phenol will be occurred as a byproduct. Actually, it is a waste material they are throwing away, and this molecule contain a OH group in the meta position. There is a C15 side chain in the R position with 1 mole unsaturation, 2 unsaturation, 3 unsaturation, and fully saturated SC15 alkyl chain. And this molecule is currently mostly using as kind of a waste material, but it is going to different places in the world. They create value-added products like paints and several molecules. Our interest is whether we can utilize such molecules to create an amphiphile, a lipid type molecule. And when the minimum condition for being a lipid is it should have a reasonable head group, it should be water loving, and it's already have a hydrophobic tail with C15 chain. It is hydrophobic, it is oil loving. And those kind of molecules with a hydrophilic head and a hydrophobic tail, we call them lipid. If it is coming from nature, we call them, natural lipid. If we synthesize in the laboratory, we call them synthetic lipid. And these lipids behaves just like a soap molecules. And if those the case, these molecules, if you mix with the water, the hydrophilic part will always love to go to the water, and the hydrophobic tail is hate water. They try to get away from water. In that case, in order to minimize the energy, how the molecules are going to arrange. And in this case, if it is in the water, if this is the amphiphile, and if you mix with the water, because the tail is hiding from the water, that's why this is one of kind of arrangement. This is the bilayer membrane. This is exactly what is presenting in our body in the bilayer membrane. And the same is, as I just mentioned, in the coronavirus. There is a bilayer membrane, lipid membrane. It is protecting the DNA, and that bilayer membranes are responsible for several functional applications. And our interest was at that time whether we can create something useful from waste material, cashew nut shell liquid, and which can self-organize. We call them self-assembly. Self-organize in water or in oil to create different kind of structures. It can be bilayers, it can be vesicles, it can be micelles, and we are utilizing the weak forces of nature. Basically, weak forces of nature means it is hydrogen bonding, pi-pi stacking, and van der Waals interaction. There is no covalent bond, there is no ionic bond. It is mostly the weak forces. Those weak forces responsible for creating this kind of amphiphilic structures. And you can see here, we created nanoscale tubular structures. We created nanoscale tubular structures and fibrous structures, helical fibrous structures, and it is very interesting. This is the first time somebody created from this kind of simple tail, single head. And this is what I mentioned. If you take our molecules, because we typically, when you do chemistry in the laboratory, if you are talking about molecules, we cannot see the molecules. But the molecules are assembling in maybe hundreds and millions of molecules are assembling. They are creating something we can see, we can touch. This is the molecules we mix with water around 80 degrees centigrade, and it will self-organize. If you cool down, they will assemble together. They come just like a piece of cotton. And if you look through the microscope, this cotton fibrous mass will look like beautiful structures at the nanoscale. And that is exactly what we are seeing here. And these are all created from simple molecules. Now, we are again interested because I showed you that in the case of cashew nut shell liquid, byproduct, the name is cardinol. Cardinol is a meta-substituted phenol with a simple OH group. We substituted that OH by a sugar or an amino acid, and then there is a tail, just like this one. There is a head, hydrophilic. There is a tail, it is a hydrophobic one. It is a lipid. And this is a lipid assembly. This is a bilayer membrane. The hydrophilic part is always outside and hydrophobic tail is inside. But the fluidity of this kind of membrane is very important in our life and in nature, especially when you are talking about plants. And there are, in Kerala, you may not understand what exactly means. In here, in the winter season, there is no leaves on the tree. All tree in the leaves will be fall in the fall season. And some plants, they can survive in the winter season as well as in the summer season without shedding their leaves. How they do that one? What they typically do is they are regulating the fluidity of the membrane. Otherwise, if it is very cold, all the leaves will crumble and the tree will die. In order to avoid that one, most of the trees shed their leaves. But few trees, they survive both time. How they does is they are adjusting the fluidity of the membrane, and adjusting the fluidity of the membrane is exactly same. This is a tail. The adjusting fluidity by changing the saturation and saturation ratio. That is exactly the same way the fishes doing the hibernation under the sea. Under the sea, the pressure is very high. In the top of the sea, the pressure is less. How they does? They are changing the fluidity of the membrane when they do that business. And that is exactly same. This, again, our friend here, this is this one, and they are changing the color. That color change is also kind of changing with respect to the environment. And thus environmental change is depending on adjusting the fluidity of the membrane. And we were interested what is happening if you have a molecule with one unsaturation, two unsaturation, more unsaturations, how they are going to influencing the fluidity of the membrane. And therefore, we use the same molecule, the cashew nut shell liquid molecule. We created an amphiphile by adjusting with a amino acid. This is a amino acid, not an essential amino acid, but it is taurine. It is called SO3H group. Most of the amino acids, we know that it is COH group. It is an SO3H group. This molecule, it is a hydrophobic tail and a hydrophilic head group. And if you mix with water, they make micelles. That is exactly what is happening when you are taking a shower or when you are cleaning your clothes. If you put the soap into the water, they create micellar assemblies. And these micelles, if you increase the concentration of the surfactants, they will go back to the vesicles. This is the vesicle. And if you change the concentration of the solution, and it will go to the bilayer membrane. And in this case, what is happening is we mix our molecules and in water. And if you increase the temperature, this micellar structure changes into different forms of assembly to arrange the energy of the system, and it is making these kind of variations at about 45-50 degrees centigrade. These micellar structures changes into these bilayer membranes, then they changes into vesicles, and then it is creating a little bit of a high viscous solution. It is kind of a jelly phase. If you cool down back to the room temperature, it will come back. It is kind of reconfigurable system to adjust to the environmental change by increase of the temperature. Just something similar. It is not chemistry. It is just something similar to this one, millipede. And if you touch it, it will go to this kind of ball shape to protect from the surroundings. And after some time, these balls will come back to the original shape. And micelles are typically very small. You can see this is under the scanning, the transmission electron microscope. This is very small spots you can see here. That is micellar representation. Here you can see this very fibrous structures, some kind of a streaks. It is an oily streak. This oily streak is typical representation of a bilayer membrane. And this much more of a big football type. That is exactly the fat ball we mentioned in the mRNA vaccine. This is a ball type. This is a three-dimensional structure. This is vesicle. And these vesicles start sticking together. It is creating a kind of a jelly face. And we observed this kind of interfacial behavior of these assemblies. And the same molecule we were trying to utilize for some other applications. You can see here, as I mentioned, I just spotted here, this is red circles are here. And these red circles are showing the allylic carbon. You all know this basic organic chemistry. Whenever you have a double bond, the closest to CH2, this carbon is in association with the 1, 2, 3 position. 1, 2, 3 position means they can resonate, because if they resonate, this carbon is much more electron dense, and these carbon hydrogens will absorb, carbon will absorb oxygen from the air, and it can create peroxides. This is a peroxide. And we all know that peroxides are highly unstable. When the peroxides are highly unstable, it will undergo random decomposition to create free radicals. According to the literature, according to the before studies, free radicals have the capability to reduce noble metals like gold, platinum, and silver into nanoparticles, or Au3 plus will convert to Au0, Ag0, Ag1 is converting into Ag0. We can create metal small particles. If you create those kind of small metallic particles at the nanoscale dimensions, they will show different colors because of the plasmon resonance. Anyway, we were trying to utilize the nature's chemistry. This is always the peroxidation is happening in nature. And though there is no chemistry we are doing, it is nature is doing that chemistry. We are utilizing those autooxidation, natural oxidation of allylic double bonds in lipid system to create free radicals. And those free radicals we utilized for reducing metal ions, especially gold and silver, using a cashew nut shell liquid based polymer we synthesize in the laboratory. As I mentioned, this peroxidation or the autooxidation is in a natural chemistry. As you can see, this is a grandbaby, this is a grandma, or grandma's hand is much more wrinkled than the baby's. The reason is, when we are all getting old, there is a little bit of oxidation is happening. It is an autooxidation or a peroxidation reaction, and these oxidation reactions will create this kind of wrinkles. And what we created in the laboratory is we created, this is a silver containing paint from cashew nut shell liquid based polymer, and this pink color is the color of the gold nanoparticles at the nano dimension. You can see this is about 15 nanometers, and if it is in the range of 15 nanometers, gold will show this pink color, and this silver will show this kind of yellowish color. We all know that silver is gray and gold is yellow, but here at the nanoscale, the color is changing. And now I am moving to the next level. Here we are talking a totally different story. If you have any specific questions, you can feel free to ask right now, or we can discuss at the end of the this talk. In gels, we are all know we are eating jellies and different kind of dessert, and there are two kind of gels. One type of gel is polymeric gels, and polymeric gels are the typical the jam and jello, or even the jellyfish in the ocean. This jellyfish is 98% of water and 2% of protein. That is what is exactly the jellyfish is. And that means any gel we are talking about, it is a two-component system. One component is solid, and the other component is liquid. Typically, the liquid is large amount. And that is another one. There are hydrogels and organogels. The most common hydrogel is aloe vera. You can understand easily. Hydrogel is aloe vera. or the starch gel when you cook rice and we are getting the liquid. If you cool it, it will make a gel most of the time. Organogel is a gel which is coming from organic solvents or organic liquid. And then grease. Most of the greases are organogels, and it is made from some kind of an oil and a solid component is there. Our interest is whether we can create simple, small molecular level gels. It is very not common. Now there are so much studies are going on. Even though we are working on water-based systems and oil-based systems, I will talk mostly about how we can convert vegetable oil or liquid oil into solid fats. Why we need these solid fats, that is to gels and delivery systems and different kind of systems. And in this case, what is going to happen is, again, we are utilizing these amphiphilic structures with the hydrophilic. This red is hydrophilic head and the tail is the black tails. This is hydrophobic tail with the hydrocarbons. And if you keep this molecule in organic solvent, what is going to happen is this red hydrophilic part is not happy with the organic solvent, and the tail is much more happy with the organic solvent. Therefore, this is a reverse bilayer. It is not the normal bilayer. It is a reverse bilayer. The head is hiding from the organic hydrophobic liquid. Because solubility, you know that like dissolves like. Here also the hydrophobic organic solvent likes only the tail, that doesn't like this hydrophilic head group. Therefore, we are always creating reverse bilayer membranes, and these reverse bilayer membranes grow in one direction. They create this kind of fibers. Suppose if you have millions of fibers, they interconnected like this one, they create a spongy structures. You just imagine a piece of sponge, and sponge which can absorb water. That is exactly what is happening. We are artificially creating a three-dimensional sponge kind of structure in water or in oil, and then the oil can congeal, which can go inside these three-dimensional fibrous structures and which can create this kind of gel. And these experiments, we do it in the laboratory using simple vials like these vials. We mix an oil with our molecules and we allow them to assemble to create some kind of a spongy structures for maybe sometimes it's 5 minutes, sometimes it's 10 minutes, sometimes it is 24 hours, all depending on what kind of molecules we are utilizing. And then initially it was flowing, it is liquid, and after some time you will see there is no flow and the gel is stable, and at that time we can invert the vial. And most of the vials, what I am going to show here, it is mostly inverted just to show that there is no flow of a liquid from here. And this is one example. One of my students created a kind of oil lamp, and oil lamp is created from simple molecules we mix with traditional oil. Now it is a kind of a candle type. And why we need to solidify vegetable oil? And that is a good question for you, because especially we use at least in our place, we use vanaspati. It's kind of a much more of a modified form of oil. And vanaspati is a kind of a solid fat. Why we need solid fat is an interesting question, because typically for regular cooking applications, we only need vegetable oil, but this kind of solid fat is necessary. One application is this one, it's kind of bread spread, and this one is again or dalda, or that is another one. And this is the butter, artificial butter from the vegetable oil. And vegetable oil, you hydrogenate it, because all double bonds in the vegetable oil is typically almost 99% of the double bonds are cis in nature. And those cis double bonds, if you artificially hydrogenate, catalytically hydrogenate, you can have saturated fat. Saturated fat is solid and saturated fat is liquid. And this kind of solid fat is necessary for different kind of application. Maybe the most exciting application is this one. In order to make, especially this is a birthday cake, whatever we are seeing on the top of this one, this white one, we call them icing. This icing is nothing but vegetable oil. It is solid fat. In order to create chocolate, you need solid fat. And solid fat is a necessary thing for making anything tasty like a cake, cookies, and chocolates. And this has been done by vegetable oil thickening process, by hydrogenation process. And this is the story. In 1910 to 1970, there are so much research was going on how we can hydrogenate vegetable oil. From 1970 onwards, industry practice utilizing hydrogenated fat or vegetable oil, they are solid, to make tasty food, including many. And that one is complete hydrogenation. Complete hydrogenation is relatively safe according to the current studies, but partial hydrogenation is a problem because right now, according to the, in the United States Food and Drug Administration, FDA, they control these food related items and the drugs, and they specifically directed partial hydrogenated vegetable oil is not good for the health. The reason is when you convert a cis double bond into a fully saturated, all double bond will convert into saturated. When you partially hydrogenated, some molecules, some of the double bonds, they will change into trans fat. Unfortunately, when we are consuming the trans fat in our body, according to the studies, the trans double bonds cannot be detected by enzymes because enzymes are responsible for digesting the food, but unfortunately they do not know what exactly the trans double bond because they never saw that one. They only saw the cis double bond in body and in nature. Therefore, the trans fat will deposit in our body. It may create health issues. And therefore, FDA said after 20, 30 years of consumption, right now it is totally banned in the United States and Europe. I believe we are still using in India. And maybe if you consider about oil, according to the studies, vegetable oil is, traditional oil is far better than the modified version. And anyway, our interest is whether we can create a healthy oil thickener rather than hydrogenation process. And in order to do that one, we were doing some interesting chemistry with naturally occurring simple molecules like tree hollows. And this is sorbitol, mannitol, and xylitol. These are all, this is the closed chain sugar. This is an open chain sugar. And all these cases are several hydroxyl groups are there. And there are primary hydroxyl groups, there are secondary hydroxyl group. Many of these hydroxyl group, they are all chiral in nature. And we are trying to utilize those kind of simple molecules which are coming from nature. These are the sources of all these sugars. And these are sugars, especially the closed chain sugars, are well studied, but the open chain sugars are less studied. As example, sorbitol, mannitol, and xylitol. I am sure that all of you know this one, and mostly you are using everyday basis these sugars, especially when you are chewing a chewing gum. Definitely these sugars are there. The sorbitol, mannitol, and xylitol. Especially why we are chewing the chewing gum. One of the main reason is to minimize the bad smell from our mouth. How it is going to happen? Mostly the sorbitol and xylitol are well known for antibacterial because they are inherently antibacterial sugars. And you look at this one, these sugars are having secondary hydroxyl group and primary hydroxyl group. Now what we are trying to do is we are taking those sugars And as I mentioned in the first place, we are always interested to create amphiphilic structures from naturally occurring molecules. We are using these sugars, we are connecting with the fatty acid. And then you're connecting this fatty acid and the sugars by enzyme catalysis. Enzymes can do the chemistry with the acid group and the primary hydroxyl group by an esterification reaction. It is a trans-esterification reaction. We make amphiphilic structures with the sugar head group and tail hydrophobic group, fatty acid. And once we have those kind of molecules, this is in the shape with the head group and a tail, and we mix with the solvent. Here it is going to be vegetable oil. And that mixing process is not that easy, because if you are thinking about soap, many of the soap never dissolves in water, but we force them to dissolve by heating or shearing. And when you cool back, this dissolved one will precipitate, but this precipitation is happening in a controlled fashion to create a very nice, well-organized structure by the self-assembly process. As I mentioned, self-assembly, we are always trying to utilize nature's forces, hydrogen bonding, pi stacking, and van der Waals interaction. And in these particular molecules, you mentioned that there are several OH groups in the sugar, and there is a hydrocarbon tail. Then the sugar molecules can assemble by hydrogen bonding, and the tail part can assemble by van der Waals interaction. They create this kind of three-dimensional, beautiful fibrous network structure, just like a piece of sponge, artificially created inside this solvent system. Then the solvent will go inside these sponge structures, and this is the self-assembly. They are making reverse bilayers. They make in fibers. Those fibers are entangled to create three-dimensional structures. And this is one of my students created in the laboratory. It is nothing but vegetable oil. This is nothing but vegetable oil. It is the self-organized with the presence of a small gelling molecule. We call them gelator, and therefore it is a molecular gel in vegetable oil. And this one, the left side, it is a caviar. Caviar is nothing but the egg of salmon, and that is very nostalgic or very one of the precious food item in Japan and many parts of the world. And this one is artificially recreated in the laboratory from vegetable oil, just to show that they both look somewhat very closer. And this is again, we can solidify vegetable oil in presence of a simple sugar-based amphiphilic structure or a simple sugar-based lipid molecule. If you mix with oil, and you can see that these are all inverted to show that there is no flow, the gel is strong enough, and this is the vegetable oil. We solidify, we are making it waxy and solid, and that is how we can create an artificial, solid fat for cooking application. This is again just showing the same molecules as I mentioned, sorbitol and mannitol. These sugars, you look at this one, there are 6 carbon atoms and 6 hydroxyl groups are there. And this out of 6 hydroxyl group, this is primary, that is the place we are going to react. And that is the only place where the enzymes activate the reaction. And this is related to what you are studying in chemistry, regiospecific. It is very site-specific. The reaction will only happen in presence of enzymes only at the primary hydroxyl group. Never going to happen in the secondary hydroxyl group. You learned about regiochemistry or reactions, and this is very site-specific, local, the position-specific. And here the secondary, this carbon is having, this is one kind of stereochemistry, and this is another kind of stereochemistry. These that is the only difference between sorbitol and mannitol. The stereochemistry of the second carbon is different. One is R, one is S. That is the only difference, but they create real changes. I will show you that one soon. And you can see we tried almost all possible vegetable oils available in our laboratory or in the shop, we buy them, we solidify them, and we can conceptually demonstrate that we can solidify any kind of vegetable oils. This is what I just mentioned. This is mannitol, this is sorbitol. The only difference between this mannitol and mannitol is an R. The chirality is R, and here, or the absolute configuration for this carbon is R. This one is absolute configuration is S, and that is the only difference between these two molecules. However, when you create an amphiphile by reacting an OH group with a tail, with a hydrophobic tail, and if you mix with this oil, the sorbitol is creating much more of a transparent gel, and mannitol is creating a much more of an opaque gel. That means only little difference in the chirality of the one carbon, we can have different kind of structures, and even you can see that their morphologies are different. One is much more of a needle kind of a fibrous shapy things. This is much more of a coarse kind of a crystalline structure, only because of one chiral center difference, R or S. And we can control this level, molecular level control. We can do engineering with this kind of systems with simple molecules. And why this morphology change is different is important in our life, especially if you are using this kind of sugar-based solid fats in our food. The taste will be different, and the taste is mostly associated with the mouth feel, how we feel in our mouth when you are eating something. Many of us doesn't like overcooked food. Why we don't like the overcooked food, whether it is rice, whether any kind of food, if it is overcooked, it is too much watery, it is too soft, and we don't feel it is tasty. And this mouth feel is very important in food industry when you are creating any food. And that the mouth feel is directly related to the structure and the texture of the material. The structure and the texture is very important, and therefore this kind of morphologies are very important. And that is exactly the reason why the food industry was trying to utilize solid fat for creating different type of foods. They can create different kind of structures and mouth feels, and they can control the taste of the food. And as I just mentioned, how these molecules in oil, these lipid molecules we created from sugars, are assembling in a solvent system. They are through the hydrogen bonding between the sugars, and they are through the van der Waals between these hydrophobic tails. They are creating these assemblies. As I mentioned, if it is sorbitol based molecule, they can create this kind of transparent jellies. But the mannitol is, if you getting, this is much more opaque. The difference is this is transparent, this is opaque. But this one is mechanically relatively weak. This one is mechanically much more robust. We thought whether we can mix these two in 50-50 or in a particular ratio, whether we can improve the transparency as well as the mechanical strength. We created a bunch of them, and we showed that we can control a little bit. And again, how we are going to see this one, because we always say we are creating beautiful structures, solid structures from simple molecules in oil, and we were watching this, how this self-organization is happening. You can see here, initially they are homogeneous. Now they are going to self-organize. They are self-assembling. They are creating a three-dimensional network by self-organization. That self-organization is right now happening under the microscope. This is the way we are seeing what is happening there. Okay, I think, let me see what is the time. Okay, I think I have a few more minutes. I will try to finish. Yeah, again, this is this is the molecules. These molecules are assembling by weak forces. They are creating these kind of fibrous structures. You can see the fibers, and fibers are entangling, and these entangled fibers can congeal, it can absorb the solvent, whether it is oil, whether it is organic solvent, whether it is water, and it is making a jelly. And you can see these fibers. Just now I showed you the optical microscope, and this is the transmission and this is scanning electron microscope, high resolution microscope. The fibers, beautiful nanoscale, maybe about 20 nanometer scale fibers are here. This is a low magnification, this is a high magnification, that's all. And this is another example, and this example is, I don't know whether you heard about chia seed. Right now in Bangalore, at least the CFTRI are promoting to the cultivation and the agriculture of chia seed. And chia is a natural healthy food and listed as superfood. And it is, they are in Bangalore, they are cultivating a lot actually, because it is known to be very healthy. And this is very similar to a mustard seed, looks like a mustard seed. And this is a seed under microscope in water. What exactly happening is, if you take this, a bunch of seeds, maybe 10% of, if you consider a liquid with 100 grams of water, and if you add 10% of seed into that one, it can solidify that water completely into a jelly material. The solid component and liquid component, they make a gel. And this is one seed under the microscope. And what is happening is, this is the story. This is chia pudding we are showing here, but if it is in India, we can easily show a faluda, especially in north part of India, we have faluda is there. And in the faluda, there are this kind of seeds, something kind of a black one you will see, that is mostly the basil seed, not chia seed in India. And basil seed and chia seed, these are the two seeds in the nature. Maybe more are there, but we do not know. And these two seeds are very common seeds which can make a gel in water if you add certain percentage. If you take mustard seed, it will never do anything like that. It will just float. But this will make a nice jelly things. And how these gels are made of, so far the belief was it is making a mucilage and jelly structure, and there is no chemistry at that time. But recently we found out that this mucilage is not really just mucilage. If you take a seed, if you mix with water, there is some kind of a fibrous material is protruding from the surface of these seeds, and they make a connection between each fibers, and it is a three-dimensional network. And these fibers are all made from simple sugars, and it's a much more of a polymeric structure, not a molecular gel. I can show you. Let me see. This is a microscopic structure. This is one seed, left hand side another seed, and there are three seeds in about a few millimeters of apart. And let me see, I can show you this is the two seeds are here, and we are putting a couple of drops of water. Now, when it is wet, the seeds from the surface of the seeds, there are some fibers are just coming out. It is protruding, just like maybe a parachute. Protrusions are coming. These are all sugar-based fibers. These fibers are interconnecting. They create a three-dimensional network, just like a sponge, and that is responsible for gelling things. Okay, let me just go. Yeah. And if you look through the microscope, you will see some of this kind of very beautiful, so fine fibrous structures at the nanoscale. And these fibers are making this network to create a sponge. This is just, I want to show you, this is also a tofu. Tofu is a solid component and liquid component. It is nothing but, the soy protein gel. It is tofu we call. And again, I will just quickly move on because time is almost up, and maybe one or two little things, then it is done. I think I can take 5 more minutes. And this is another example, maybe something very exciting and interesting, how we can make amphiphilic structures from simple molecules which are coming from nature and which could be potentially applicable for herding chemicals. I don't know whether you ever heard about herding. Herding is much more of a biblical word. It is mostly for pulling animals using another animal, or a pulling another, just like maybe in India, in Kerala, it is a much popular scenery, at least in the past. People with the duck, they come with maybe a pole and they are kind of pulling the ducks together, and that is a herding process. It is in the animal kingdom. If you have so many sheep or animals and you can pull together, and there are dogs are there, I will show you that one. But in chemistry, whether we can use one type of chemical to pull together another chemical, that is called chemical herding. It is a relatively new term we use in the oil spill industry. Whenever there is an oil spill is happening in the ocean, because most of the oil drilling or the rigs are in the ocean. In Mumbai, in Mumbai High, there are so many oil, drills are there, rigs are there. If there is a oil spill happens there, and many of the oil spills are happening under the sea, because there are different kind of oils. There are some oils are very thick, some of them are very thin. If its density is very high, nobody is going to see what is happening under the ocean. But the density of the oil, there are different kind of oils, and if the density of the oil is less, it will come on the top of the ocean. Then we see, oh, there are oil spills. There are several oil spills are happening everyday basis all over the world, but some of them are known, some of them are not known. And there are several ways of mitigating these oil spills, and there are chemical methods, there are mechanical methods, and there are other kind of methods. One of the most latest one people are still studying, nobody is using right now yet in the industrial level, but there are studies are going on using a surfactant, and which have the capability to pull together the oil and then they burn it off. If the oil was everywhere here, there are chemicals are spraying around, then they're collecting the oil, then later they burn it off. That is the only way to mitigate this oil spill, unless otherwise all the fishes will dead and the plants will dead. And therefore, especially this kind of oil spill recovery is specifically applicable for if there is a very thin layer of oil. You might have seen this kind of thin layer oil. If there is a kerosene spill is there, you will see a thin layer of oil on the surface of the water. Whenever there is oil is there is no oxygen beneath that one. It is harming the plants and planktons and the fishes. And this can be how we can control this one. What typically they does is, if this is the oil spill, this is the oil, this is the blue is the ocean. Why the oil is spreading? Because the interfacial tension of this oil is, the interface means the interface between the oil and the water. This is the interface between the air and the water. At the interface, the surface tension of this oil is less and the surface tension of water is high. Therefore, the water is dragging the oil in everywhere and the oil is moving in this direction. If you can reduce the movement of oil in the right hand by applying certain kind of a surfactant which have the high surface tension, then the oil will retract. And this is what is exactly a certain family of chemicals. They can have very and the surface tension is reducing and the oil is retracting. And at that time, typically helicopter will come and put the fire and burn the oil. And this is a pictorial representation, or in other words, if there is an oil spill, there is a water. If you're applying a certain family of surfactant, the oil cannot move, oil cannot spread, then we can remove that one. That is exactly what we are trying to do. In order to do that one, we need to synthesize a surfactant which has the surface tension around 30. The surface tension of water is 72, and a surface tension of 30 means those surfactants have the capability to reduce the spreading of the oil on the ocean. And we were trying to utilize a alcoholic structure from nature. This is a byproduct of chlorophyll. And chlorophyll on degradation, we are getting this kind of isoprenoid structures, and these isoprenoid structures with an alcohol, and we introduced a ionic part. This is a hydrophilic part, this is a hydrophobic tail. And these surfactants have the capability to reduce the surface tension around 30 of water from 72 to 30. Those kind of surfactants are generally known as herders, very low surface tension. There is only one system is available currently. It is a polymer. It is a siloxane-based polymer. The people are looking for, the industry is looking for naturally occurring, environmentally friendly, sustainable molecules. This is one example. What we showed is, I will show you that one. This is what I mentioned, how we can pull together animals using any kind of a tool. Here, this is a dog. This dog is German Shepherd that is kind of, running around, and they are pulling the animals. Here, we are trying to utilize the molecule we synthesized in the laboratory to pull together the oil. This is a laboratory experiment. There is a pan, and this is a plastic pan, and we are trying to fill with crude oil. This is a crude oil from Gulf of Mexico, and it's a low density oil, and we are trying to create a thin oil layer here. We are trying to mimic the oil spill. Let me see, I can just fasten it a little bit. The oil is spreading, and once oil is spreading, according to the theory, if it is in the ocean, the helicopter will go and spread this particular surfactant, harder surfactant around the surface. And here we are just applying our molecules in a very small scale in the surrounding area. Now we have, now we have a thin layer. Now we are applying from here and applying from here, and you can see how fast we can collect the oil using a couple of drops of salt, the surfactants we created. It is shrinking and shrinking. At the moment, we are trying to watch them by video, and we will calculate the shrinking process and thickening process. And in order to catch, maybe you could have asked a simple question: why don't we just put the fire on the original thin layer? If it is very thin layer, according to the standard, the minimum thickness of the oil should be around 3 millimeters. Otherwise, it won't catch the fire. And that is one example. This is the last one. We are done. And as I mentioned, we are always interested to create throwaway battery, a battery, because right now we are using the lithium ion battery in our cell phone, one of the best example. And theoretically, this lithium ion battery contains cobalt, one of the component. Cobalt is toxic. We are supposed to recycle it, but nobody in the world except a very low percentage of batteries are recycling. Most of the batteries we are throwing away with a toxic chemical cobalt. Our industry is whether we can try to mimic and create a battery which does not have any toxic chemicals like cobalt, whether we can create a battery from an organic molecule. This is one example. This is a molecule which is coming from henna. We all know that what is henna is, or the melange, and this molecule is called lavzone, and we used one example is that one. We use that lavzone molecule. This is another molecule. This is called purpurine. This is purpurine is a molecule coming from the roots of a plant in India or in Middle East. and we used that one, we did, but henna may be more interesting. A common tattoo chemical for energy storage. We used that lavazone molecule, the basic component of henna, and we dimerize it, and which have the capability to bind with the lithium, and I will show you. And then this is the lavazone symbol molecule. We made the dimer, we made the tetramer, and these are all by simple one-step chemical reaction in ethanol. It is very simple reaction, and these molecules have the capability to bind with the lithium with this carbonyl group and OH group, and they can be reversible when you apply voltage. And very interesting chemistry, we conceptually showed that a molecule which are derived from this lavazone or the henna are capable to show excellent battery performance, and still we are interested to create this kind of sustainable and throwaway battery. And also we are trying to study how they are intercalating or coordinating with the sodium or potassium or lithium or other metals. Also we are continue to do, and which includes basic organic chemistry, then electrochemistry and theoretical calculations to understand the fundamental chemistry of this one. And the TKL, the tetrakis lavazone, 4 lavazone molecules together capable of binding 3 sodium, and it is 4 lithium. Just by lithium and sodium there is a big difference, and electrochemistry is in par with the current lithium ion battery, and we are trying to understand more chemistry, we are designing them. And finally the story is, even though I took a couple of minutes additional, finally the story is whether we can create materials from renewable feedstock, something useful and interesting, and it's much more of a sustainable molecular design as biomass as a platform. And for the most important is to acknowledge my students and collaborators, as well as somebody who is helping us with funding the students as well as the laboratory, and these are different places we are getting funding. And finally, thank you for attention, and sorry for taking more time. And right now this is I'm happy to answer any questions if you have, especially from students, and looking forward to, I'm sure that you are eager to go for the dinner. Thank you very much.
Thank you very much, sir. The presentation was very informative, and Professor John has explained very well how to make the new materials from the waste. Any questions from the audience?
I spoke about several things. Please feel free to ask anything.
Chat box. Sir,
yeah, please.
You have synthesized antimicrobial paints, no?
Yeah.
Have you calculated the shelf life of that antimicrobial paint? Is
that
it
part, I think it is, actually we don't compare those one, but I believe we can optimize those kind of situations, because at that time much more we were interested in chemistry, and we created the stuff, and we studied almost everything, the antimicrobial capability, but shelf life we haven't studied.
As there are no more questions, let me take this opportunity to thank Professor George John for this wonderful and informative presentation. Really, the presentation was very colorful. Thank you, sir, and thank you very much.
Thank you very much. Thank you, everybody. Good night.
Thank you, Dr. George John, for the informative talk. Thank you, Dr. P.M. Saburabegum, for chairing this session. With that, we have come to the end of the third day of MATCON 2021.
Okay, I can leave. Yeah, now I can see you. I can, I cannot hear you. Yeah.
Okay, fine. It was a wonderful talk.
Yeah.
Very nice,
You're
as
welcome.
always.
Thank you very much.
What? Maybe the nth time that I'm attending to your talk, and every time it has gone on improving. That's what I should say. Very good.
Oh, thank you. Yeah. Thank you very much. Yeah.
All right.
Yeah.
So I
Yeah.
think it's already late.
Then, have a good dinner and a happy, good night. Yeah.
Okay.
Thank you, Professor Pradhavan. Thank you, Professor Begum and Dr. Nabil. Thank you very much.
Okay then.
Yeah. Okay.
Yes,
Bye-bye.
Bye-bye.
See you. Yeah. Leave you. Yeah. Bye-bye.